Okay, the content of my talk will be, but it works this. There is no.
No, it's on the contract.
On the contract. Okay, okay, okay. We will outline a brief description of Galileo's system, but everyone knows. The ingredients which make Galileo particularly suitable for science, for example, the presence of both of two clocks of different kind, PHM, passive hydrogen meson, and rubidium. The unhappy event of Doresa and Milena, two Galileo placed in a very highly eccentric orbit. The second generation of Galileo upgraded with scientific payload, the plan to upgrade the second generation of Galileo with new scientific payload, and the possibility to realize, to establish a cellular network fully devoted to Galileo for orbital tracking. Currently, the SLR tracking is performed under the umbrella in the frame of the ILRS service, that is a service based on a voluntary base and cannot give operational continuity. In the second part, then we will describe how Doresa and Milena can be helpful for investigation in the field of fundamental physics. Then we will briefly discuss how, with Galileo clocks, we can catch dark matter. And then finally, we will describe how, by means of Galileo, it's possible to perform atmospheric sensing by means of radio occultation. What is the added value of Galileo? Okay, let me, I skip this part. Galileo, this is the space segment of Galileo, 27 sparse satellite plus 3 sparse satellites. This is the age of Galileo, and this is the inclination. Each satellite is guaranteed for 12 years of lifetime. Okay. This is the signal structure of Galileo. We have 3 bands, very large bands, and these are the signal encrypted on the carrier of Galileo. We have bulk and alt-bulk signal, very special, particularly suitable for reflectometry investigation, for bistatic investigation, while this signal is the B-phase keying signal that we have on GPS. Okay. This is the highlight of the status of Galileo. This information were provided us to by Javier Ventura Traveset, by ESA. This is the situation of the deployment of Galileo satellite. In 2020, the constellation will be fully operational, while in 2026 should start with the second generation of Galileo. These are the orbits, the orbital positions of the satellite currently along the 3 different orbits. These are some products that Galileo is able to provide. For us, is of particular importance, this product, that it defined the frequency accuracy against the UTC of Galileo time system, and it is performed at a level of almost 2 per 10 to minus 14, as is declared by the specification of the bot. The clocks we have. This is the heart, of course, of Galileo. GNSS generally are timing systems. We have the rubidium and the passive hydrogen maser. With rubidium, we have a frequency stability of 4 to 10 to minus 40 over 10,000 of second, while the stability of the PHM is at less than 10 to minus 14. These are the potential payload that Galileo can host aboard. It planned to host enhanced environmental monitoring units for space weather investigation, accelerometer, VLBI transmitter signals, passive active laser retroreflectors. In particular, the active laser reflector will be capable to synchronize remote ground clock over intercontinental distances. And Galileo, which hosts the GNSS receiver, just for sensing atmosphere and other things. There will has been developed a ground infrastructure in support of science at GSAC in Madrid, and the GSAC decided to establish an SLR ground network fully devoted to Galileo satellite. This is the news that they gave us just in the last meeting of Galileo Science Advisory Committee. These are the challenges for Galileo that have been outlined in a technical note of Galileo Science Advisory Group. Essentially, the scientific activities on Galileo will regard fundamental physics and dark matter, the study of gamma ray bursts to improve the geodesy and geodynamics level of investigation, time and frequency system to improve the time and frequency system, put on board new clocks, and put on board also payload able to study ionosphere scintillation. Then another field of activity that, on a scientific point of view, Galileo wants to encourage is monitoring of neutral atmosphere and climate change, reflectometry, etc. In particular, in my presentation, we will focus on the first part, fundamental physics and dark matter, and in the second topic will be the monitoring of neutral atmosphere and climate change by using radio occultation activity. Brief history of Doresa and Milena. Doresa and Milena were launched on 22nd of August 2014, but were injected in a highly eccentric orbit. There were to maneuver in order to recover the nominal orbit, but the best things that we were all able to do is to put on board, to put in an orbit, in a resonant orbit of 37 times 20 37 orbits for 20 days at an at a semi-major axis almost close to 28,000 of kilometers, and an eccentricity, a very high eccentricity, 0.15, with respect to the injected, initially injected eccentricity that were 0.23. This is a study performed by ASI, by the Italian Space Agency, and this was the last solution, was the solution that ESA implemented. So we have now two satellites on orbit over at 28,000 kilometers of semi-major axis with an eccentricity of 0.15 This is a sketch, an artistic sketch of the different orbits of which we are talking about. The green is nominal orbit, the red was the wrong orbit, the blue is the last orbit of the Doresa and Milena. Now, so we currently we have a satellite with two highly eccentric orbit. But why satellite with highly eccentric orbit can serve fundamental physics investigation? This is the Bible. I prefer to take the. I will focus on the. This is the osculant terms are the Gauss equation that ruled the change of orbit due to the perturbation. If we look at the osculant term that regarding the perigee, we have that the perigee depends on the inverse of the eccentricity. So for very small eccentricity, we have perigee that is not is not possible to determine because it's very unstable the solution. Another singularity is regard the node in which we have the scene of the inclination. But now, if we have a high eccentricity, we can work also on perigee. This is the simple idea. Okay, this is the equation of the perigee in which are involved the radial distance, the radial component of the force of a perturbation acting on the satellite. The along track is given by T, and the normal is given by the, where is the normal? There is the normal. Okay, but the normal component is just perpendicular to the orbital plane. And in perigee, we have the radial and transverse component of the perturbation. What we can measure, essentially, we are not able to measure directly the perigee. We measure the eccentricity vector, and which errors is given, as I told before, by the eccentricity, semi-major axis, and the uncertainty on the perigee. Of course, this is confirm what I told before. A small, very small eccentricity induces a very high error in the determination of the perigee. In this, if the perigee can be measured, we have more parameters to exploit for to perform scientific investigation. And perigee is particularly important for effect due to the general relativistic effect. These are the different, the correction, relativistic correction applied to the GNSS system and also to Galileo. We have, of course, the gravitational frequency due to the Earth mass. We have the gravitational frequency due to Earth quadruple moment of the Earth. The second order Doppler effect due to clock velocity. This is a special relativistic effect. A periodic relativistic correction that we apply just to take into account that the orbit of the Galileo, nominal Galileo, is not perfectly circular. And then we have a Sagnac correction due to the fact that we have the displacement around the Earth between the satellite and the clock reference on the ground. The first experiment, the natural experiment that we have in mind when we have very high values of the perigee is the gravitational redshift. The last measurement of the gravitational redshift was performed by means of the Gravity Probe A mission that confirmed the effect at the level of 10 to the minus 4. Before there were experiment of Pound and Rebecca in the 1960s that confirmed the experiment at 1% of level. If we look at the orbital parameters of Galileo, semi-major axis of 28,000 of kilometers, a precision of the orbit, stability of the clocks at a level of 10 to the minus 14, and eccentricity of 0.15, we could have a confirmation of gravitational redshift at a level of 10 to the minus 5. And in fact, in the great project that was completely devoted to the measurement of gravitational redshift, a work performed by Observatoire de Paris at the University of Bremen, they improved the gravitational redshift of a factor in turn of 5.6, the French part, and 4.0 for the German part. These are the publication in which have made public this result. We plan to do the same measurements, and we are starting to work about this, but we would do other experiments, not only the gravitational redshift. For example, we would measure the perigee shift. This is the classical measurements related to general relativistic theory. And we have, on the perigee of the Galileo, a part due to the gravitoelectric field, the precessional perigee that we, for example, have measured for the first time on Mercury. And this is a term due to the gravitomagnetic Lestring effect. The value of the Schwarzschild precession of perigee is at the level of 436 milliardsecond per year. It's a really big effect. While it's not so the same, but this could be not a drawback for the perigee of lens steering that is only minus 5.4 milliardsecond per year, essentially are about 75 centimeters expressed in length. In 12 years, the perigee precession of Lagius 2 was estimated at 2.5% level of uncertainty, but Lagius 2 has an eccentricity 10 times smaller than Galileo, and so we are confident that by using Galileo eccentric satellite, we will be able within 10 years to improve the measurement done with Lagius 2. Another, what is the approach? Before to continue, I would explain what is the precise orbit determination approach to measure this so tiny and subtle effect. Essentially, we solve the orbital motion in dynamic mode of the satellite with over arc that are partially overlapped. We switch off in the software the effect of a general relativistic effect that we want to measure. So we would have the general relativistic effect by studying by accumulating the residual between the arc that are partially overlapped. And in this way, we plan to measure the effect that we want to pursue. Okay, now let's move to how to measure gravitomagnetic field. Is by far the most intriguing measurement, because we are speaking about very small effect, but help us some improvement that we had in the meantime. A lot of satellites are ranged now at centimeter level of precision, both by SLR, GNSS, and Doresa. We have had a tremendous improvement in gravity field of Earth, thanks to the mission like CHAMP, GRACE, and GOES. So the perturbation due to the classical thermogravitation are no more a problem for us. And finally, we have conceived some algorithms, the so-called gravity field-free algorithms, that minimize the effect of gravitational error to enhance instead the signal of the fundamental of the parameter that we want to measure. And last but not least, just the unique scientific opportunity to have GSAC 5 and 6, the eccentric Galileo, without eccentricity, that make measurable the perigee as well. The lens steering measurement is really challenging, but as JFK would say if he were here with us, we choose to go to measure lens steering in this decade and do the other things, not because they are easy, but because they are hard. Okay, anyway, a first proposal to measure the gravitomagnetic lens steering effect was the Lagos 3 mission. It is simply conceived a twin satellite mission like Lagos, but placed in a supplementary orbit, because the classical gravitational field depends on the cosine of the inclination. So in the supplementary orbit, we cancel the classical gravity field disturbances and enhance the general relativistic effect. But Lagos 3 never was launched. And so in the 1996 was launched Lagos 2, that had just the same problem of Galileo. It was placed in a highly eccentric orbit, for a wrong highly eccentric orbit. And we will attempt for the first time to use the perigee 2. And we perform a gravity field-free combination, so essentially for lens steering as well as for the perigee. What they disturb are the event zonals of the gravity field that have a secular trend. So if we cancel the contribution of the event zonals by means of a combination of the parameters, the perigee, the node, the Lagos 1 and the Lagos 2 and the perigees of Lagos 2, we would able, three parameters, we are able to cancel two event zonals in order to minimize the gravity field uncertainty. This was the principle. Okay, in the past, there were not pursued this strategy, the combination of satellites, because we believe that LEO satellites were disturbed a lot by other perturbations like tides, solar radiation perturbation, and atmospheric drag. So they were not considered suitable for fundamental physics measurement. But this is not true, because yes, the perturbations are huge, but they have a shorter period. So for a long time of integration, these short period terms cancel out, vanish. And so they can use also to measure fundamental physics parameters. Another negative comment was, but the general relativistic effect on MEO satellites are too small. But this is not true, because what is interest for us is the ratio between the signal and the noise. And for radios that at 5,000, 6,000 kilometers high from Earth, we have a signal to noise at a level of 1.2 per 10 minus 9, while for Galileo, this signal to noise is lowered is halved. Okay, so the idea why we don't use a lot of satellites with a lot of orbital parameters that can cancel out the event zonals of the gravity field. And so we have added also the Galileo in eccentricity orbit, eccentric orbit, 3 minuti. I'm sorry. I'm sorry. Okay, and we have applied the gravity field free approach just to cancel with n parameters, n minus 1 event zonals. And these were all the parameters that we conceived. As you can note, we have at last also the perigee of the eccentric Galileo. Okay, this is the way how to manage the uncertainty. I skip. And this is the table of the combination. As you can see, we have a family of combination in which we have involved essentially Etalon satellites. That is a satellite at an 8 very close to GPS and Galileo. Then we have another family of satellites in which are involved the Galileo and the Galileo eccentric satellite, and we have a third family, one that in which involved Lares, that was the satellite just designed to measure the lens steering effect. It, as you can see, is not among the best combination able to measure the lens steering. It appears only after 30 best combination, and this is the level of uncertainty, very close to the uncertainty that we have found. That is confirmed by the observation where the measurement was performed at 5% of level. Then we have the Yukawa-like interaction, but I skip because now the time is almost over. Okay, then we can establish a relativistic positioning system, and these two Galileo satellites can be the first two satellites devoted to the new relativistic positioning system. Okay, we skip for the non-gravitational perturbation, and the most important, most challenging for what concerns Galileo. Solar radiation pressure is the only surface force that acts on the Galileo satellite. There is no atmospheric drag, the tides are very small, but the solar radiation pressure is particularly dramatic for Galileo, and we plan to model them. Okay. Okay, I skip because, okay, we skip. This outlined the importance of SLR observation. This is the time solution that the clock solution that geodesists achieve routinely, and as you can see, when there are eclipses, we have disturbances. We are that the errors increase just in this phase. The use of SLR could help to model in a proper way the perturbation just in this transition phase and improve also the clock solution. And this is important, of course, also for our STAR investigation about fundamental physics. Okay, I will skip. Now let's move directly to dark matter detection. I skip the how the dark matter detection, why dark matter detection was a problem. We have in a cosmological field a Robertson-Walker matrix, which depends on the density of the universe. There is a critical density if the density is major of this the critical density, we will have a big crunch. If on the contrary will be less than 1, we will have an expansion, a definitive expansion of the universe. The first to find the dark matter was the Fritz D. What is it? I don't know, Zwicky, Fritz D. Zwicky, an astronomer that studies, investigate the cluster of galaxies, and found through applying the Virial theorem that there were a dark matter, a matter without light. This now is confirmed by the gravitational lenses and through this phenomena we are able to determine what is the quantity, the amount of dark matter. Okay, this should be, but now look at, okay, vabbè, okay, there is, doesn't work. It is not a problem. What we, Rubin and Canford observed that the velocity of the star around the galaxies were much more higher than expected if we look only at the light masses present in the galaxies. And she explained this different behavior with the presence of dark matter in galaxies in a halo well beyond the light halo of the galaxy itself. Then Ostriker and Peebles, by using a simulation, confirmed this strange distribution of the mass in the galaxies. We have evidence also all over the world in the universe that the excess of mass. And what we have currently, we have that 73% of our universe is made by dark energy, 23% of dark matter, and the rest is due to the baryonic mass that we know. Okay, what are the suspected dark matter? We have brown dwarfs, brown small galaxies. This is the last entry. And then we have, for a while, investigated about the weakly interactive mass particle, very small mass particle, that could constitute the dark matters. Just in the last years, we have investigated the presence, if there is in the universe, there are topological defects, string, monopoles, and domain walls, 2, 1, and 0 dimension. And the topological topological defects were formed during the cooling of early universe through a spontaneous symmetry breaking phase transition. Now it's time to leave the hunting of the flies, and it's time to embrace elephant, to catch dark quantity of dark matter, more massive dark matter. How we can detect these topologic defects? These topologic defects, when are crossing our solar system, they change the fundamental constant. The dimension, the fine structure constant, for example, the ratio of the light quark mass to the quantum chromodynamics energy scale, the mass of the electron and the proton. The dimension of these topological defects are ruled by the Compton wavelength, and they can range from 1,000 of kilometers to 100,000 of kilometers, just the dimension of our solar system, our Earth system. How we expect to detect dark matter that is in transit. They produce a coordinated changing of the frequencies and the time tagged by the clocks when they are transiting through our solar system. We expect that the velocity of this transit is about 300 of kilometers per second. This is what are the papers on which we have, from which we have taken the figure. What we have to measure is the coupling constant and the quadratic scalar coupling that we plan to measure. And we have to understand if these quantities are over the error threshold of the frequency or the time that we are of the clock that we want to measure. These are the shifts that could induce the dark matter transit on rubidium and cesium. Okay, this is the value of the field. I'm sorry. This is the value of the field, which depend on the discretized pseudo frequency built by using GPS data. And we have a threshold of the error of about 0.48 nanoseconds and 0.56 nanoseconds. But a work of Roberts, Blewett, and others have used 16 years of data, but they didn't find dark matter. Now, I sleep. With the clocks of Galileo, they plan to have an uncertainty at the level of 5 to 10 to minus 12 seconds. They plan to measure lower this threshold. But the question is, but Galileo can improve these measurements? In principle, yes, because we would have AGS clock solution that are at level of 20 picoseconds better than the value used by Robertson and Blewett, and we have that the Galileo clock are more precise over level 5 or 10 with respect to the GPS. But this is, in principle, cannot be possible because in a work it's stated that the change in fundamental physics depends on the number of the weight of the atom. Higher is the number, atomic number of the atom, higher is the effect of the dark matter. So it seems that passive hydrogen measure cannot be helpful for this measurement. This is the plot that describes what I'm saying. So it is hopeless to use the Galileo to improve this measurement. But this is not true if we, and the different clock, PHM and RAFs sensed a lot the passage, the transit of dark matter. PHM, no. So, but we could have the direct control on the GPS, on the clock on the satellite directly without using a geodetic approach in which that introduce error in the ranging due to the atmosphere, orbits, and so on. If we would have direct information of the clocks on board the Galileo without using geodetic approach, we would able to, essentially we have two clocks, one is sensible and the other no, we could detect the dark matter with a level of precision 2 or 3 orders better than done by Robertson and Blewett. And with this I finish because the time is finished. Thank you very much for your attention.